Newton's laws of motion define the concept of a force. That's a phenomenon which causes a mass to accelerate. While Newton only studied one of these forces, the universal force of gravity, he's established a protocol for looking at all the other forces in nature. In lecture 11, I'm going to tell you about two of the most ubiquitous yet complex phenomenon in nature, in our daily lives. That is magnetism and static electricity. One of the great and surprising principles of science is that magnetism and static electricity are forces that can be either attractive or repulsive. My objects in this lecture are to describe the historical developments of understanding the phenomenology of magnetism and electricity, which seem to be two very different forces. For magnetism, we're going to focus on natural magnetic materials, the Earth's magnetic field, and the behavior of compass needles. In the case of static electricity, we're going to look at the concept of an electric charge and review the behavior of charged objects. In subsequent lectures, then, we're going to find that electricity and magnetism, these seemingly unrelated phenomena, are indeed closely related. They're intertwined. But in this lecture, that won't be quite clear yet because we're looking at this from the historical context, and in the early days, people didn't recognize this connection. Before beginning the exploration of electricity and magnetism, let's review where we've come in the first 10 lectures of this series. In the first 2 lectures, we examined science as a way of knowing, as a process for asking and answering questions using that scientific method of observation, pattern recognition, hypothesis, theory, and then prediction, which led to more observations. These are the 4 steps of the idealized cycle, although in many cases in the natural world, scientists have to use intuition and make intuitive leaps of kinds that wouldn't be strictly dictated by that scientific method. The next 2 lectures explored how the scientific method was used by a whole succession of scientists to develop the modern view of the heliocentric, the sun-centered solar system. New observations of planetary positions led from the Ptolemaic Earth-centered view to the Copernican model with circular orbits, and then to the realization by Kepler that orbits are in fact elliptical. Isaac Newton and his universal laws of motion and gravity were the subjects of lectures 5 and 6, while the last 4 lectures have examined energy, the ideas of the first and the second laws of thermodynamics. Throughout these lectures, we've touched on the concepts of mass, of motions, of energy, of forces, and these are the central attributes of the physical universe. One of the most important and mysterious forces in Newton's day was magnetism, which causes one end of an iron needle to accelerate in the direction of the Earth's North Pole. The study of magnetism was, of course, of extreme importance 500 years ago because it was an age of ocean exploration. And the compass was the key tool in preventing you from getting lost, especially in days when the sun and the stars were not visible. So the compass, this simple device, a device which has a magnetically aligned needle, which points to north and points to south, this simple object has played such a vital role in the discovery of the natural world. Magnetic rocks called magnetite or lodestone were discovered by ancient Greeks. They were discovered in a region of Asia Minor called Magnesia. And so these rocks that attract pieces of iron, where you actually can pick up paper clips and so forth with a rock, this naturally occurring material began the study of magnetism. Magnetite's an abundant ore of iron. It's found all over the world, and so it was widely available to the ancients, and the phenomenon of magnetism, therefore, was understood and observed quite early on. A few basic features of magnets are well known to the ancients. A magnet suspended by a string, for example, can pivot, and if you have a second magnet, you can apply forces to that. You can see the forces acting as the magnet swings around under the influence of a magnetic field. The compass, then, is merely a magnet that's suspended on a pivot point, and it can swing around in the Earth's magnetic field. When 2 magnets are brought together, you find that opposite poles attract each other, what are called north and south poles, but like poles, 2 north poles or 2 south poles will repel each other. You've probably had that experience if you ever played with magnets. It's a great thing to do with your kids, to get a set of magnets and see how they behave. A piece of unmagnetized iron, like a nail, can be magnetized simply by stroking it with a magnet. This is something else you can do. You can take a powerful magnet and take a nail and just run the magnet along it a few times, and that nail then, if you do it enough times, will become a magnet, even though it was not magnetized before. Perhaps the first researchers to conduct extensive studies on magnets were the compass makers themselves. And you can imagine why that's true. If you're going to build compasses, you have to understand how magnetism works. You have to understand how to magnetize needles and so forth. One such craftsman was Robert Norman, who lived from about 1550 to 1600. Records on these early instrument makers aren't so precise as those for scientists and people who publish things. Norman was an instrument maker, and so as a tradesman, his records are not so well preserved. So very little is known about him. We know that he was for many years a British sailor, and that he became a maker of navigational instruments following that career as a sailor. Rather than simply duplicating the design of others, however, Norman attempted to improve the seagoing compass. He then wrote some of his experiences in a book called The New Attractive, published in 1581, and this described the curious tendency of a compass needle to dip. The dip is somewhat of a nuisance to compass makers. This is the tendency of a compass needle not only to align itself north and south, but also to adopt an angle dipping into the earth. Norman describes an experience trying to make a compass needle and the frustration. This is while he was trying to correct a particularly beautiful and elaborate decorated needle. You can imagine these iron needles with all sorts of engravings and beautifully incised and shaped and so forth. And he had created such a needle for a very elaborate compass, and the trouble is it kept dipping down, touching the bottom of his compass, and so it didn't work very well. Here's what he said: "I cut it too short, and so spoiled the needle, wherein I had taken such pains. Hereby being stricken into some choler, I applied myself to seek further into this effect." Well, he didn't just get angry, he got even. He began to study the dip or the declination of the magnetic needle. What he did was a very clever idea. He took the needle and he put it through a cork, so it was precisely balanced. He then had it floating in water, and the needle then would orient itself in water. It would actually orient itself up and down. So he was able to measure the magnetic needle by exactly balancing the weight of the needle in water. Norman concluded by suggesting that the compass needle acquires a virtue in spherical form extending about the stone. And the idea of this virtue extending about the stone was the first real suggestion that there was such a thing as a magnetic field, imaginary lines extending out from the magnetic object, which then interacted with the Earth's magnetic field. He also saw a very practical side to this magnetic dip that he was studying. He realized that since the dip varies with latitude on Earth, it might provide an extra navigational aid. You could actually use the dip of the compass needle to help locate where you are, not just north and south, but also how far north you were or how far south. Various ideas about magnets were synthesized in the research of the English physician and physicist William Gilbert, who lived from 1544 to 1603. Gilbert must have led an amazing life. He graduated with a medical degree from St. John's College in Cambridge. That was in 1569. That's about the same time that Tycho Brahe was making his first observations of the heavens, the astronomical observations, and at that time Galileo was just 5 years old. This is a very exciting time in the history of science. He began practicing medicine in London in the mid-1570s, and by 1581 he was one of the most prominent physicians in the city, rising to the presidency of the College of Physicians in London, a very distinguished position indeed. In 1600 he was appointed personal physician to Queen Elizabeth I. He served in that capacity until her death in March of 1603, and William Gilbert died just a few months later of the plague in 1603. His great scientific work is De Magnet, published in 1600. Gilbert catalogs the properties of magnets. He demonstrated that, for example, that every magnet has two poles. He also showed that broken magnets, you can take a magnet and break it again and again and again, and every fragment of the magnet also has a north and south pole. Gilbert proposed that the Earth itself is a giant magnet with its own field, with its own north and South Pole. And to test this idea, Gilbert constructed a sphere of magnetite, of that natural magnetic material, and documented the nature of the magnetic forces around this spherical object. This kind of field with a north pole and a south pole is called a dipole field, a two-pole field. The Earth, the Sun, many other bodies in the heavens have this kind of dipole magnetic field, and so do any magnet. Any magnet has a dipole field, a north and a south pole, so arranged. So that's called a dipole. The Earth's magnetic poles don't correspond exactly to the rotational north and south pole. The Earth rotates on an axis, and that defines the north pole and the south pole. The magnetic pole, however, is several degrees off, and it wanders slightly. It moves around from year to year. And furthermore, over long periods of geological time, perhaps once every 500,000 years or so, the Earth's magnetic field has this remarkable property of actually flipping. The Earth's north pole ends up near the south, and the south pole ends up near the north. And this flip occurs perhaps on average once every 500,000 years. We'll talk more about that when we talk about plate tectonics later on in this course. The idea of the Earth's magnetic field flipping and moving around is very important in the field of geology. Some volcanic rocks freeze in their magnetic orientation of the Earth when they cool, because volcanic rocks have little magnetic minerals, in fact magnetite, that act as compass needles. When the magma, the volcanic rock, is liquid, those compass needles orient to the Earth's magnetic field, and then those orientations are frozen in. So the cold volcanic rock has its own magnetic field. It tells you what the magnetic field of the Earth used to be many millions of years ago. And this information is used by geologists to understand the variation of the magnetic field from over the millennia. Norman and Gilbert had clearly introduced the idea of this magnetic field, but it wasn't until the early 19th century that a gifted British experimentalist, Michael Faraday, he lived from 1791 to 1867, and we're going to hear a lot more about him later on. He performed a simple demonstration of sprinkling iron filings on a magnet, and I'm sure you've seen these illustrations of iron filings forming beautiful patterns outlining the magnetic field lines. That was a 19th century discovery by Faraday, who liked to do public lectures in science. You see complexly curving field lines. They stand out starkly in this sort of experiment. And they're not simple lines radiating out from a point, as we talked about in the gravitational field, the idea of lines just moving straight out, but rather the field lines curve around from pole to pole. Along that axis, force varies over distance squared, just like electricity and magnetism, but they're curving field lines. Along other directions, the force exerted can be extremely complex. The force is a function of the size and shape of the magnet, as well as the position of the object, for example, pieces of iron within that dipole field. So the exact description of the magnetic force with a magnet, especially a curving magnet like a horseshoe magnet, can be quite complex indeed. Much more difficult to describe and model mathematically than the force field coming out of a gravitational object like the Earth. Many mysteries about magnetism remained in Michael Faraday's time. One persistent question is whether it's possible to have a magnetic monopole, that is, a single north pole or a single south pole in an object. And that question is still very much with us today. Another very big question for Faraday and his contemporaries is what exactly causes a magnetic field in the first place? And to answer that question, we have to wait until we learn a little bit more about electricity in the next lecture. Okay, now I want to shift gears, and we're going to talk about the other great force, the other great phenomenon that people studied in these early years. It wasn't obviously related to magnetism anyway, and that's static electricity. This is a subtle, yet it's a pervasive force in all our lives. You get static cling. You get frizzy hair on a dry winter day. Lightning is static electricity. The little sparks you feel when you shuffle across the room on a cold day and you touch a doorknob, that's static electricity. In the 18th and early 19th century, static electricity was a curiosity. It was a natural phenomenon of little practical concern, but perhaps still worthy of philosophical investigation, because Isaac Newton had said anytime something happens, there's a force involved, and clearly something was happening with static electricity. One of the people who studied static electricity in the early period was William Gilbert, who did so much to improve our understanding of magnets. He found that some substances become electrically charged when they're rubbed with fur or with silk. Amber, glass, some minerals, for example, also have this process. More rubbing produced a greater charge. And we can demonstrate this quite easily with a very simple illustration. You can take a couple of packing peanuts, those little styrofoam balls you get in the kinds of packing that you receive in packages in the mail. You just wrap them with aluminum foil and suspend them with a string. Then just take a comb and run the comb through your hair a few times, picking up static charge, and you'll see that the comb then causes attraction, and then you see there's a force involved here. Something's happening. This isn't gravity, this isn't magnetism, that's something quite different. And so you can study this force. It turns out that some materials, which are called insulators, hold this electric charge, whatever that might be. Other materials, especially metals, don't hold their own charge, and the charge drains away from these conductors. Those substances are like metals and wires and so forth. You notice that in this particular arrangement, we have insulating materials with this suspended, what are called pith balls. You have a string that hangs down that's insulated, but a little piece of conducting material at the end, which is insulated from its surroundings. It turns out that charges can be passed from one object to another just by touching. And you saw that with a comb combing through your hair. You touch one of these pith balls, as they're called, and you see the charge passing from one to another. You can transfer charge by rubbing a piece of fur or glass, various combinations, and you can also get this transfer of charge from one object to another. One of the most efficient and effective ways of doing this is something called an electric friction machine. In these machines, you have a belt of rubber or cloth or fur that's spun rapidly against another substance. And as that spinning occurs, you strip off a great deal of charge and develop very high electrostatic charges. Such machines were used well into the 20th century. Things called Van de Graaff generators were used to develop extremely high voltages for high-energy physics experiments. So these weren't mere curiosities in the 20th century. They were the best way to develop very high voltages. Electric friction machines, however, were first used for parlor games and novelties. A great novelty in the 18th century was called the electric kiss. What you'd do is you'd have a group of people standing around this friction machine holding hands, and a young engaged couple would be at opposite ends of the people. And as you cranked up the electric friction machine, you'd develop a very high voltage. The two people would kiss, and a spark would pass between their lips, and everybody would jump. Let me read you a historical account by the American historian Bernd Dibner. This is another example of using an electric friction machine. An electrical discharge was sent through a company of 180 soldiers of the Royal Guard before the King of France. This occurred in the courtyard of the Palace of Versailles, and the shock sent all the men leaping into the air at the same time, much to the glee of the king and his party. So dramatic was the demonstration that the king had it repeated in Paris using 700 Carthusian monks, who all jumped into the air together when jolted by an electric shock. You can actually use one of these electric friction machines. I've brought one with me today and will subject myself to its terrors. You merely turn the intensity up, and you see a belt moving here, and as I lean over, oh! You can get quite substantial shocks out of this. And perhaps my hair is also standing there. So I'm developing quite a voltage there. And we'll leave it at that. So this is a way of generating very high electrostatic charge by rubbing a belt against another machine. That's just an electric friction machine. It's been around for hundreds of years. Electrically charged objects exert forces on each other. And you can study these forces in a systematic way. And once again, the way that people did this, to really study this systematically, was to suspend various objects that could develop a charge from strings and so forth. And they could do this very systematically. I'll show you again. Look very carefully at what happens. You charge up the comb, and at first you get an attractive force. You see? But then once the object gets touched, after that attractive force, then it seems to be repelled. And so we have a very odd situation here of a force that is at once, it can be attractive and it can be repulsive. So the electrostatic force differs from gravity in that way, that it can be both attractive and repulsive. What's happening here? Turns out that Benjamin Franklin, the great American statesman, the great ambassador to France, the person who played such an important role in drafting the Declaration of Independence, signer of the Constitution, and so forth. He lived from 1706 to 1790. It was Benjamin Franklin who was best known in his own day as a scientist, as a physicist who studied this electrostatic phenomenon. He was called one of the leading electricians of his day. That was the title they gave to people who studied these electrostatic phenomena. Let me tell you about Ben Franklin. He's an amazing character. He was born in Boston in 1706. He received his early education in Massachusetts, but is best known for his activities in Philadelphia, which was at the time, believe it or not, the second largest city in the British Empire. Philadelphia was second only to London in size. Franklin founded the first library in America. He founded the first fire department in Philadelphia. He was extremely active in the city life there, in both the state of Pennsylvania and also, of course, in the American colonies as a whole. Franklin gained great fame as a successful inventor, notably of the Franklin stove and then later of the lightning rod, about which I'll tell you. If you had asked educated Europeans about Benjamin Franklin in the 1760s and 1770s, most would have known of him, and they would have known of him for his scientific work. Franklin suggested that the electrostatic charge, the electric charge that we saw here, is a kind of fluid. It's what we now call electrons, although Franklin did not know that, and that was not discovered until a good century later. A material becomes charged when friction removes or adds this fluid from one object to another. So a normal object that you pick up, like a comb, is balanced. It has a neutral amount of this fluid, exactly enough fluid. But if you comb it through your hair, then Franklin wasn't sure, one object or the other, either the comb or your hair is gaining more of this fluid and the other is getting less of it. And so each become charged. The hair becomes charged, the comb becomes oppositely charged by the transfer of this one kind of fluid, which should be in balance, but in a charged object, it's not. The behavior of these balls then can be understood by Franklin's idea. When you first charge an object, the comb is charged. The ball is not, but the fluid in the ball, that is the ball's electrons, are distorted by the comb's electric charge. At first, the ball is attracted to the comb, but then they touch, and both objects are charged. Then they repel each other. The initial attraction is because the ball that's uncharged has the fluid moving away from the charged comb. So it gets pulled in, and then suddenly it has an excess and it gets pushed apart. So you have the attraction and repulsion both shown by these two objects. Franklin was an eminently practical man. He recognized that certain materials take electric charge and transfer electric charge, and other materials were insulators. And he realized that you could apply this knowledge to protecting lives, to saving lives, through the invention of the lightning rod. The lightning rod is such a simple idea. Franklin realized that lightning was a form of electricity, of this electrically charged object. In fact, it's said that Franklin went out in a thunderstorm with a kite, with a metal string, to actually prove to himself that lightning had this kind of electrical property. I don't think Franklin did that experiment, although others did, and showed beyond a doubt that lightning was a form of static electricity. So if you could find a material that would safely conduct that fluid away from your house down into the ground, you would prevent houses and other buildings from being hit by lightning. And that's what the lightning rod did. It's just a simple piece of metal, a metal wire, which goes from the roof of your house down into the ground, therefore conducting the electrical fluid away from the house. And it was this understanding of the electrical fluid that allowed Franklin to make this great invention. You can quantify the forces that are involved in these electrostatic demonstrations. There is a force involved, and through very meticulous and careful experiments, you can measure the exact amount of force, you can measure the way it varies with distance and with the amount of charge and so forth. And that was left to the job of Charles Coulomb, who lived from 1736 to 1806, a great French physicist who conducted meticulous experiments on electrostatic forces. And he determined the exact force law between two charged objects. Force equals the product of two charges divided by the square of the distance between them. The equation, force equals a constant, charge of the first object times the charge of the second object divided by distance squared. Does this equation look familiar to you? Does it remind you of something else? Well, indeed, this equation is very much like that for the force of gravity. A force is present only if there are two charged objects, just like in the gravitational force, you need two masses. The force is inversely proportional to the distance between the two objects, just like gravity. There's also a constant there. In the case of the gravitational constant, it's that big G we talked about a few lectures ago. The same sort of thing is true for the electrostatic force. The law for electrostatic force, though, is different from gravity in two important ways. First, the electrostatic force can be either attractive if you have opposite charges, or it can be repulsive if the charges are the same. And that's different from gravity. Remember, gravity is always attractive. The second difference is that the electrostatic force is vastly greater than gravity. A cone with just a few billion extra electrons can pick up a piece of paper against the entire gravitational pull of the Earth. So your own experience with static clean, with frizzy hair, is that this electrostatic force is vastly greater than gravity. In these equations for gravitational energy for electrostatic forces, we use the concepts of mass and we use the concept of charge. We can measure these quantities, but their physical origins still remain obscure. What is it about an object that gives it this ability, either the charged object or an object with mass, to exert forces on each other? That's still a very subtle point. You might think that static electricity isn't a central topic of physical research these days, and that's probably true to a large extent, but we do have to deal with the consequences of static electricity all the time. We have lightning, we have to deal with that. It occurs whenever you have agitated rain, very turbulent rain, up in the high levels of the atmosphere, and you're actually stripping electrons away from the upper levels of a cloud, and then the electrons get concentrated as the base in water droplets, and as the rain falls, you're transferring electric charge from the cloud to the ground. Lightning is merely a way of compensating for that charge that's being transferred from the upper levels of the atmosphere down to the ground. You can have cloud-to-cloud lightning in these situations, you can have cloud-to-ground lightning, and even in rare situations, ground-to-cloud lightning. So all different situations where you have an unbalance of charge leads to lightning. Often the ground itself is not going to have a net charge. You say, well, why would lightning go from a charged place to something with zero charge? What happens is you have the attraction, remember, of oppositely charged particles. So if, for example, if the top of the cloud is negatively charged, the ground is induced to have a positive charge. The negative charges in the tops of trees, for example, are pushed away, and that leaves a residue of positive charge. So you induce a charge in the ground even though the ground does not have a net charge. And that's why lightning tends to hit the highest objects, church steeples or trees, other tall objects. If you're in an open field, you better get away if there's a lightning strike, because you're going to be the tallest object around and lightning will look for you. There's an important technological use of static electricity in our everyday lives. That's the Xerox machine. And let me just tell you briefly about that. A fascinating object, the Xerox machine. You have a rotating drum. That drum is made of a special material that takes a static charge. When light shines on part of the drum, that static charge is eliminated. That part loses its charge completely. But therefore, if you shine a black and white pattern onto the drum, that black and white pattern is reproduced in the static charges on the drum. The drum rotates by a pile of very tiny plastic beads, which are by static electricity attracted to the charged parts of the drums, but not to the uncharged parts of the drum. And that black powder, that black plastic, is then impressed onto a piece of hot paper. The plastic melts onto the paper, and that's your Xerox copy. So Xerox machines use static electricity in a very basic way. By the way, if you want a darker copy, you just merely turn up the voltage, you get a higher static charge. If you want a lighter copy, you turn down the voltage, and you get less of that black powder attaching to the drum. Okay, in summary, let's review what we've learned about these two seemingly unrelated phenomena, magnetism and electricity. Magnets always display two poles, designated north and south. This situation is called a magnetic dipole. When two magnets approach each other, opposite poles attract, like poles repel each other. The Earth itself is a giant dipole magnet, so magnetized compass needles point to the North Pole. Static electricity is a force that occurs between two electrically charged objects. Negatively charged objects have an excess of electrical fluid or electrical charge, what we now call electrons. Positively charged objects have a deficiency of electrons. Opposite charges attract, like charges repel each other. And this situation leads to many phenomena, lightning, Xerox machines, and so forth. Static electricity is interesting indeed, but the true practical importance of electricity was not realized until scientists began to study electric charges in motion, the phenomenon of electricity, which is the subject of the next lecture.